Welcome to Module 12D in Physical Science. We'll be talking about resistance, switches, and circuits. Our vocabulary: the word resistance, open circuits, series circuit, and parallel circuit. So what is resistance? An example of resistance is your experiment 12.3 in your text. A strip of aluminum foil is held to both ends of a battery with your thumb and a finger. The strip is held until heat from the foil causes you to drop the battery. This heat is a result of electrons flowing from the negative side to the positive side of the battery. The electrons begin to collide with the electrons in the battery begin to collide with the electrons in some of the aluminum atoms. The collisions produced the heat felt in the experiment. That heat felt in the experiment was a result of the aluminum resisting the flow of electrons. Each metal resists electron flow differently. Consequently, each metal has its own resistance. The type of metal is not the only thing that determines resistance. The size of the metal also is important. A wide piece of metal has lower resistance than a thin piece of metal. Take a look at this picture over on the right side. If we were to make this thinner, you can see that we would be compressing the electrons and the atoms together so they had less space in between them. They could move less freely. If we made the piece of metal wider, then there's more room for the electrons to move and more quickly. A wide piece of metal has lower resistance than a thin piece of metal. There's less resistance because there's more room to move. The number of electron collisions is reduced when there's more room for the electrons to spread out. The longer the metal, the more chance the electrons have to collide with things in the metal, so the larger the resistance. Metal's resistance can be used to convert electron energy into heat and light. The type of metal used will influence the resulting effect. Most metals will resist the electron flow in a way that will produce mostly heat and only a small amount of light. So those metals would be the ones that would be used in heaters, stoves, and toasters. Think about what a coil looks like on the top of an electric stove. Other metals can produce more light than heat, and these metals would be used in the filaments of light bulbs. Now, electrical devices don't use up electrons. And that's something that you intuitively think will be happening, that they'll all be used up. The same number of electrons flow out of a toaster as that number that flowed into the toaster. What the toaster does use up is energy. The toaster uses the energy produced as colliding electrons flow through a circuit. Let's talk about switches and circuits. When we see circuits, a good example would be light on the wall in a room. We think of circuits as being something that's closed, like the pictures we've seen before, but actually sometimes they're not closed. Here's an example over to the left that shows an open circuit. You can see to the right side of this drawing that the wire is not touching and that there's a gap. An open circuit is a circuit that doesn't have a complete connection between the two sides of the power source. So there's a break in the wire, and the metal doesn't link the two sides of the battery or the power source. The electrons can't flow from side to side because they can't jump over the gap in the circuit. Consequently, there would be no current in this circuit. Now, if I push the piece of wire down to join the wire below, the circuit will be closed and current would flow. So here's how a switch controls electricity. So over on the left, we see a picture of a light bulb hooked up to a power source, and this light bulb is not on. The reason being is that the switch is open. When the switch is closed, you have a complete circuit and the light goes on. When you flip the switch on the wall, you change the circuit that powers the light. So when the light is off, the circuit is open. When the light is on, the circuit is closed. There are different types of circuits. We'll begin with discussing what a series circuit is. And most of you have encountered this, and usually this has to do with strings of Christmas lights. Maybe your parents have an old string that's been around for a while, and when one of the bulbs goes out, the whole string goes out. Well, the illustration here shows you something similar. You have a string of light bulbs, and here's your power source, and one of the light bulbs is broken. Because that light bulb is broken, the other light bulb won't work. The broken bulb breaks the connection, the electrical connection for the entire circuit. When you replace this broken bulb with a good bulb, the circuit is repaired, it's closed, and the lights will both go on. That can be really problematic, particularly when you're doing something like wiring a house. You want to make sure that you don't have one light go out in a room and have all the other lights go out in a room. So then what you would do is wire the house with parallel circuits. In parallel circuits, the problems with series circuits can be resolved by hooking lights up so that each one is independent. It stands on its own, but at the same time, there's also a flow of current going to both bulbs. You can see this in this drawing. The current begins and it's traveling and it goes to the first bulb, and it also goes to the second bulb. So even though the first bulb is burned out, it doesn't break the circuit to the second bulb, and that one is still working. So if you have any questions, be sure to contact me. We're almost at the end of this module. We only have one more video, and we'll talk at you soon.